n is 0, then n cannot be 0. And then we have the sum where m is not 0, and then n can be anything at all. Okay. Up to this point, actually, I could have let k be odd. As long as k is bigger than 2, even if k were odd, this is an example of a modular form. The catch, though, is if k is odd, then the pair n and minus n cancel out. And so you just get the 0 function, which is consistent with the fact that it's the only example of a modular form of odd weight is 0. Here k is even, and we're going to use that right here. Since k is even, the terms at n and minus n are the same. And so I'll write twice the sum, n at least 1 over n to the k. And here, again, if m, the whole inner sum, since k is even, if you have the sum with an m over all n, and the sum with a minus m over all n, again, it's the same series over all n, where the m and the minus m are considered. And so, again, I can write a sum over double the sum over all integers, 1 over m tau plus n to the k. Okay? Now, here, in this part, every tau has a non-zero coefficient. And so, term-wise, each of these go to 0. So you would expect, you would hope, that the whole thing should go to 0. And all you should be left with is this leading part here. So let me just erase this piece, this previous calculation. So we expect that as tau goes to infinity, we expect to be left with just the first term. And to justify that, and so this really is correct, to justify that, I'm just going to go back over here and say, I mentioned that the Eisenstein series converge uniformly on compact subsets. Actually, it's a little bit better than that. They don't just converge uniformly on those little closed bounded sets, but they even converge, if this is the upper half plane, if you take any kind of strip that's away from the boundary line, the real axis, if you take any infinite strip going up from some point onwards, within some range up, it actually converges, the series converges uniformly on this infinite half strip. And that's good, because the infinite half strip kind of surrounds infinity all the way up at the top. And since the series is invariant under tau going to tau plus 1, if you just look at the values of the Eisenstein series, say from 0 to 1, or minus a half to a half, you're going to pick up all the values. And so if you just focus on the strip, say from minus a half to a half on up, the series converges uniformly all the way up, and therefore you can that justifies this just formally plugging in infinity and making everything 0. Okay? And so we see that the Eisenstein series actually has a limiting value. In particular, it's bounded. Okay? So these are the basic examples for each weight 4, 6, 8, 10, 12, and so on. We have one example of a modular form of that weight. Not by a long shot is this the only one up to scaling. If I have a modular form, you look at the definition, and I multiply it by a non-zero constant, multiply by a 0 constant, but we've been there before. Multiply by a constant, it's also a modular form. But you can have modular forms of the same weight that are not scalar multiples of each other. But here we've only constructed a single example in each weight. So these are the Eisenstein series. Now, I said that the only modular form of weight 2 is the 0 function. But what's wrong with, why can't you just set k equal to 2? So if you set k equal to 2, this series is not absolutely convergent. And infinite series over a doubly indexed, unordered set, if it's not absolutely convergent, you don't want to deal with it. So, there really is, the math is consistent. You really can't work with this when the weight is 2, although we will see shortly, well, maybe in tomorrow's lecture, how you can almost give a meaning to this when the weight is 2, and it really is useful. But for now, we're just going to, of course, pass over in silence what's going on when the weight is 2. So this construction of a modular form is by writing down an explicit infinite series and checking the conditions. Often, if you look in books, they don't reduce to the case of two equations to check. You could verify directly that Eisenstein series satisfies the modularity condition for all A, B, C, D, and SL2Z directly. You don't have to reduce to the case of only two equations. But if you're going to, what was I going to say? Yeah, if you want to construct more examples, well, the construction by these series is not how most examples are thought of. So the usual way that people write down or think about or work with modular forms is using what's called their Q expansion. So I want to explain what that means, the Q expansion of a modular form. So then I'll come back over here. Since I want to probably go back to that equation later on, so I'll leave that up on the board. Are there any questions? Yes?
What were you explaining with the being between -1/2 and 1/2?
I was saying that to justify that as tau goes to infinity, you can just termwise let tau go to infinity in each term. I was just saying that to justify that, you would like to talk about the convergence of the Eisenstein series, not just in a little bounded set, but in a set that includes numbers really high, arbitrarily high up. And I said the convergence is uniform, not just on compact subsets, but even on infinite half strips. And since the function at tau plus 1 and tau are the same, its values everywhere, you just focus on any strip of width 1, and you'll pick up all the values there. So if you want to look at the behavior of a modular form, all modular forms, in this, our definition, the values at tau plus 1 and tau are equal. And so you could just focus on the strip of width 1 and look at what's happening as tau goes to infinity in that range. Any questions? So the Q expansion of a modular form is also how modular forms show up in combinatorics, physics, partition functions, generating functions, and string theory. Some of these are modular forms, and they arise, I believe, as Q expansions. Is this? Who's the physicist? Is this true? Yes. Okay. So maybe we'll find out more about this after class. So we're going to talk about the Q expansion of a modular form. So here's the deal. Every modular form satisfies this equation and this equation for some weight. Okay, you get modular forms in different ways, but modular form weight k satisfies these two equations. This is not the definition of a modular form. It should be analytic, and it needs to have behavior, suitable bounded behavior as tau goes to minus infinity. If you see the three conditions in the definition of a modular form, they're independent of each other. You can write down functions that satisfy two of them, but not the third one. So you really need all of them together. I should say, why do we care about these three conditions together? Modular forms of a given weight 4, weight 10, they're a vector space. You can add and scale them, and they still satisfy the three conditions. And it turns out that they are a finite dimensional vector space of functions. You can calculate their dimensions. And it's this fact that there are lots of areas of math and physics that give rise to modular forms, and when different constructions land in the same little finite dimensional space, you can kind of discover unexpected relations between them. And so if you drop the conditions, any of the conditions of being a modular form, like I don't care if it's bounded at infinity, I just want to think about these equations. Well, sorry, like the analytic function of the upper half plane that satisfy these equations, and you just ignore the boundedness condition, that's an infinite dimensional space. Not saying it's not interesting, but the finite dimensionality of the modular space of modular forms of a fixed weight really needs all three of those conditions. So here are the two algebraic equations that we think of when we have a modular form. I want to look at this one, the one that doesn't even have the weight showing up in it because the fudge factor just becomes a 1. So as complicated as modular forms might be, this equation on its own has a very simple example of a function satisfying. It's not a modular form. The function e to the 2 pi I tau. And it turns out that we can think about a modular form not as a function of a point tau in the upper half plane, but as a function of a complex number of this form. So how does that work? So here's the upper half plane. Here's a point in the upper half plane. If you look at the function, as usually called q, is e to the 2 pi I tau, what happens? Well, if tau is x plus iy, then e to the 2 pi I tau, if you do the algebra, do the math, turns out to be e to the minus 2 pi y e to the 2 pi I x. Right? Because you have to multiply tau by I, brings the y to the real part, with the minus sign of the 2 pi. Notice, as x varies, it's kind of moving around in angles, but y is positive, and so we see that q, the complex number e to the 2 pi I tau, has absolute value less than 1. Since y is positive, we have a minus sign there. Okay, so this is q has absolute value less than 1, is not 0. It's between 0 and 1 in magnitude. For all the points in the upper half plane, e to the 2 pi I on the points lands in the punctured unit disk. And it doesn't take on the value 0, but every other point in the open unit disk is a value of e to the 2 pi I tau, and the ambiguity, when do a tau and a tau prime have the same q value? Well, exactly when they differ by an integer. Right? They differ by 1, differ by 2. Okay? We understand the kernel of the exponential function. By the way, when did we start officially? Bobby has no idea. And we started a little bit late, so we're going to go on a little bit. I'm just getting like 50 minutes here. So, because the function doesn't change if you replace tau by tau plus 1, and the only way 2 points in the upper half plane can have the same e to the 2 pi I value is when they differ by an integer, and when it's equal up to a shift by 1, it's equal up to a shift by any integer. So what it means then is it's well defined to define a new function on the punctured unit disk to be the old function of tau, where you write the point if you write the point in the open unit disk, punctured open unit disk, as an e to the 2 pi I tau value, it doesn't matter what tau you use because it's only ambiguous by an integer, and the modular form doesn't know the difference between shifting a number by an integer or not. And so functions on the upper half plane can be thought of as functions of e to the 2 pi I tau instead of tau itself. Does that make sense? Because the value of tau and tau plus 1 are equal. So we can convert a modular form into a function on the punctured unit disk. So for example, as tau gets huge, that means y gets big, that means q gets small, that corresponds to q going to 0. Okay? And notice I'm not saying anything about this equation. This equation is very hard to express in the language of e to the 2 pi I tau. But the first equation lets us write any function on the upper half plane that satisfies the first equation as a function on the unit disk. So it turns out that this is an analytic function. And so therefore, it's an analytic function on the punctured unit disk, not including 0. But I said, remember the third condition in a modular form? It's that the value of the modular form is bounded as you get high up, which means if you think about the modular form as a function on the punctured unit disk, then as q gets close to 0, the value is bounded. Now, in real analysis, you can have functions like the absolute value that are smooth away from 0. It's bounded near 0, but it's not smooth there. But in complex analysis, there's the fundamental Riemann removable singularities theorem. you have an analytic function around a point, except perhaps at the point, and it's bounded, the function is bounded around the point, then actually the function has a well-defined limit at the point, and if you extend the definition of the function to the point by using the limit value, that's an analytic function there too. So in fact, the boundedness of a modular form as tau gets large is actually equivalent to the convergence of the function as tau gets large. From this point of view, there has to be a limit as q goes to 0, translates back, and there has to be a limit as tau goes up to an infinity. And so in fact, what it means is a modular form can be extended to be, from this point of view, an analytic function of the whole open unit disk, including the origin, and therefore we can write it as a power series around 0. Okay? I'm not saying it's an easy process to see what this series is supposed to be, and by abuse of notation, we even write the original modular form, the same letter. We say it's a function of q, it's a function of tau, it doesn't really matter. And so every modular form, ignoring the second equation, just using the first equation, every modular form can be written as a power series in e to the 2 pi I tau. So this is called the Q expansion of the modular form. We'll see next time what the Q expansion of the Eisenstein series turns out to be. I want to stress, though, that anytime people talk about modular forms, they usually talk about their Q expansion, these coefficients. They like the constant term. The constant term is that limiting value of the modular form as you go up. Okay, so I know the constant term of the Eisenstein series is Q expansion. The constant term will be twice the sum of 1 over n to the k. On the higher coefficients, not so clear. But this construction, this Q expansion, this way of writing a modular form, has nothing to do, doesn't easily exhibit the second condition, the weight f of minus 1 over tau equation. And so if you're given a random infinite series, it is completely opaque about whether or not it's actually the Q expansion of some modular form. Writing a modular form as a Q expansion is a very standard way of representing them, but it hides the second equation in the modularity condition that actually includes the weight. It's very hard to express the transformation in the second equation in the language of Q. Right? Anytime you write something, it's automatically it's invariant that the tau goes to tau plus 1, but the second thing is very hard to see. So next time, I guess we'll start by writing down the Q expansion of the Eisenstein series. The last thing I want to say, just so that it's helpful for the plenary talk that will be later today, is that I've defined modular forms for the group SL2Z. But you can define modular forms for subgroups, finite index subgroups of SL2Z. In the modularity equation, you could include some funky root of unity scaling factors on the right-hand side. And I think that's all I want to say. Oh, and the last thing is that in the modularity condition, for us, the weight is an integer, but there are many important applications where the weight of a modular form can be a half integer, 1/2, 3/2. Okay, let's go back to the 19th century. So there are many important examples of modular forms of what are called half integral weight, not integral weight. But they're very subtle objects, theta functions of quadratic forms and things like that. So we'll see some examples of those in the plenary talk. And we'll also see, I'm sorry, I just read one more thing. Well, no, I think I'll just probably stop here since we're already a little bit over time. So we'll continue with this next time. That's all for time. So.